Welcome back to another HVAC Engineering Techie training video. Today is the first video on design. So today our video is on basic HVAC systems design, which is video D1. And I've started working on the design ones, which will go from HVAC, and there's 4 videos in that one. It'll go to electrical. There are several videos in that, and it may go beyond that. I'm not sure yet. I'm still thinking about that, but anyway, this is exciting for me to start talking about design. So remember, this is the channel that talks all things HVAC and building systems. I appreciate you being a subscription member. It really helps me. If you're not, I really appreciate you become one. Just hit the subscribe button down below. Give me a thumbs up. It helps me because Google uses that to evaluate the videos, which keeps me on the air, and I really do appreciate it. I do appreciate you guys watching the videos. So have fun with this one. D1, let's get started on HVAC design. So this video is on HVAC design. Might be a little confusion of exactly what that is, but this video covers the design process for HVAC systems used by designers, technicians, and engineers. It is not intended to provide engineering education or engineering technique. It is only for the purpose of educating on design basics. You all realize that engineering is a big subject, and you can't do it in 4 videos. So we're just going over the basic process, and so it'll help, but it's not intended to make an engineer. This is not going to happen. This video covers basic HVAC design process to produce construction documents, what those documents really need to have. Reviews traditional basic HVAC load calculations performed by engineers. I realized that my education was a long time ago, and I worked as a designer for many years ago. And the world's kind of moved on, and everything's computerized. And the problem with that is that some of the younger folks know how to use the computer, put input and get output, but can't tell if there's a problem with the output because they don't fully understand what's happening under the hood. So basically, on load basics, we're going to talk about what happens under the hood, what is being done by those programs that you're using. Review basic HVAC duct design process and layouts. Review basic HVAC pipe design process and layouts. Review how equipment is selected to meet engineering calculations. Now, I think I've told you guys this before, but I started out in design and worked 8 years in design. Then I became a mechanical contractor, then became a test and balance contractor, and then I became a commissioner. That was over many years. So I have seen all aspects of mechanical systems and electrical systems, basically from all the way from design, all the way to commissioning, trying to make them work, all the way to helping owners trying to operate them. So my view is a little unique. And some of the things I will tell you is what would be very valuable to the people in the field if you will give them that data. So hopefully you appreciate that. This video is intended for HVAC designers, obviously, HVAC commissioners who should understand some of the design processes, HVAC technicians and control technicians. This can be valuable for them as they go through their daily activities to kind of understand why it was done that way, or how they can explain if they see a problem. Starting HVAC engineers seeking more practical knowledge. I realize that when you go to college and you get your engineering degree, you come out, most of you know absolutely nothing about HVAC because there's very few colleges in the U.S. that actually have a robust HVAC engineering program. They teach basic mechanical engineering, no problem. You come out with your sub-minor in mathematics, you understand that, you've got physics, you have all that stuff, but you don't understand HVAC. And the reason I'm able to say that is because when I was in design, one of my jobs was as a new engineer trainer. And so I realized that there's a bunch of information you need that you don't have. And this video will certainly help you get that basic stuff that they didn't teach you in college. Because you already know all thing about engineering, but now we need to tell you about design, which is actually a much different thing. Some people believe that engineering is design, and it's not. It's totally different. The designer is about practical, putting it on paper or putting it on not paper anymore, but making sure the drawing is actually ready to go and someone can actually build from it. Okay, what do we have? What does HVAC-Techie offer to support this? And of course, this first video is D1, is basic HVAC system design. I realize this subject is big enough you can't put it in one video, so I've split it up. D2 is calculating HVAC loads, exactly how you do those calculations. D3 is airside equipment and duct design. Duct design is half art, half engineering. It's got some things you need to be aware of. D4 waterside equipment and pipe design. And then we have a bunch of general videos that support these design videos with general education. And E2 is basic physics, temperature and heat calculations. E3 is HVAC heat load calculations for technicians, and it walks through a spreadsheet heat load for simple stuff. E4 is airflow and pressure calculations. E5 is psychometric repair. E6 is water calculations. E8 is altitude effect on HVAC. E10 is how to calculate outside air, which should be obvious, but I got to tell you, I do a lot of design reviews, and outside air is a big problem. S1 to S22 is all about all the HVAC systems. So, you know, if you're a young commissioner, or if you're a young designer, or if you're a young engineer, you need to understand the systems that we have traditionally used and the ones we're using today. And these videos will go through what those systems are, how they basically function, what their basic sequence of control is, so you can understand how they're utilized. P1, understanding HVAC efficiency. Kind of a boring video, but it does go through how that we determine efficiency. Basic HVAC design. So what about the design process? Well, the HVAC design process workflow is the same no matter what type of system or what tools you use to calculate loads, select equipment, or size duct and pipe systems. So the process is the same. It doesn't matter what tools you're using. Standard workflow from the start of the project to 35% review. Now, most projects have a set review process, so the owner can review the progress of the design. And normally those are a schematic design, which on most jobs is a 35% review, and a 65% review, which is the basis of most of the design, and then a 95% review, which is, are we ready to produce CDs, construction documents? So we're going to go through what you do to get to each stage of those. You know, part of the game, and I see a lot in design reviews, is normally the amount you get paid is based upon meeting these milestones. So some people push to get to this milestone. They'll say, we got a 65% set here, and it's really about 40. Or we're at 95, and you're not even at 65. So we need to understand what actually goes in these. So in the 35% review, we need to select the system type, obviously, calculate building block loads for cooling and heating, create a preliminary zone layout, very important, calculate zone cooling and heating loads, which are, of course, different than block load, and we will go through that in the calculations. Create a preliminary system layout. Select main equipment to meet load requirements. Run an integrated modeling load program based on the assumptions of horsepower. You don't know yet, but you're assuming those to determine basic energy usage. And this will happen, of course, if you have a green building or if you have an owner that requires this. Develop 35% design development layout drawings, which are simple drawings. You know, the architect gives you background drawings for 35%, and all the major equipment is located, and you may show duct and pipe layout single line, just rough sketches of what's going to happen. Create a preliminary basis of design document, a BOD, a narrative document for 35% review, and we will go through what that is. So standard workflow from that 35% up to 65%, revise the 35% design based upon review comments. Select an air distribution, grills, and registers. Now, remember this, as you go through this review process, the owner reviews the documents. If they have a commissioner on board, he'll review the documents. Code officials may review the documents. So there's a lot of different people look at them, so you'll get comments back. And some of those comments are good, some of them are not, some of them are irrelevant. And you may have to learn how to answer those comments in a respectful way that says, no. It's hard to do, but you have to understand that you're developing a design that you have a lot of understanding for. And just because someone makes a comment doesn't mean you have to change, but it does mean you have an issue you need to address. And so it's not that hard, but you need to do that. And as commissioners, we only learned one thing really easy. Always ask a question. Don't make a statement. A statement tends to get people's backside up, and a question is something they can answer. So you always ask everything in a question. So you select air distribution grills and registers, select the zone temperature control devices, size air distribution duct systems, 65%, size hydraulic or refrigerated distribution pipe systems, create specifications and drawing schedules for selected equipment, develop 65% HVAC design development drawings, develop 65% 3D drawing Revit files if it's required. If your contract requires that you're doing 3D modeling, then you need to produce those. So here's the deal: the 65% is basically the design is done. You just don't have the document ready for construction. It's at 65%. So this is where you need to have. This is the big review. This is the one that we're not going to change much after 65% review. So 65% is a big one. Review space utilization conflict with other crafts. And this is, if you have 3D modeling, this gets a little easier because the model will show you crashes where you're conflicting with space allocation. To do that, you have to have everything sized. So all the ductwork has to be sized, and all the pipe has to be sized and laid out, or you can't run a crash program. So develop 65% HVAC design specifications. Create 65% control drawings. Now, at this stage, at 65%, sequences should be there, basic sequences, basic control drawings. So in other words, the design is pretty much complete. There may be a few details still not there, but this should be enough that someone can say, I understand what we're going to get from these drawings. Create 65% sequence control for each standard system. 65. Now, what's the standard workflow from 65 to 95? This one's not too tough, actually. It revises 65% design based upon review comments. Again, this is 65% was the big review, so you should get the most of the comments coming back at 65%. Need to answer all comments, all of them. Even if it's the ones you don't like, you still have to answer them. Finalize all specifications and drawing schedules for selected equipment. Finalize design development drawings. This may be important here if you're working as a seam at risk or something like that, where the costs are being developed at the same time, and so some cost aspects may affect the specifications or drawings, and you may have to deal with that. But that's done at this level. Finalize HVAC design specification, finalize control drawings and specifications, run a final integrated model load program to determine energy usage. So at this point is where you're going to run that final model, because you have all the horsepowers, everything is settled here, so you need to do that. Review 95% documents for full communication of the design, and we will talk about this. What I'm trying to say is, how does this design communicated to the contractors and to the operators? Sometimes we forget there's a number of people that depend on these drawings to do their job. One, of course, the contractors. They need to know how to build and how to build it. But also there's commissioners need to understand what you're trying to do so they can actually test the systems correctly. And then you have building operators. You have test and balance guys too with the commissioners that need to be able to test the systems correctly and balance them correctly. And then you have operators that need to understand how to operate this system. And we fail a lot at that. We build drawings, we say, well, they can build it from this, but we don't actually tell the operators how to operate. And we'll go through this when we talk about communicating the design. It's really important, and it's not that hard to do. It just has to be aware. So standard workflows from 95% to 100% CDs. Review the 95% design based upon review comments. Answer all review comments again, just like the others. Turn the design development drawings into construction drawings. Nowadays, with AutoCAD and everything, it's really easy. Basically change the title and hit a button and you're done. It's easy when everything is digital. Turn the design specifications into final construction specifications. Verify construction notes on drawings. You make sure, and one thing I always complain about that is I know we're all trying to make money and we're trying to, in a hurry, do things, and we use a lot of standards. But make sure your standard notes and standard details actually match this project. It's really hard for a contractor when you look at the detail and you look what we got, they don't match at all. And what are you supposed to do? Well, you have to generate an RFI. So this creates more work for the contractors, and it creates more work for you. Now you got to answer an RFI, all because you've got to look at the notes. standard workflow for construction services. So if your contract calls for the engineering firm to provide engineering services, there are certain things you do during the construction of the document. And these will be different depending on your contract. Review contractor equipment submittals. That's almost always included. Attend key coordination meetings as per contract requirements. Answer RFIs as they come in, request for information. Provide a written response with any required sketches or other design data as required to answer the RFI. Now, you know that RFIs are required if there's going to be money involved. If the answer is going to involve additional money, there has to be an RFI process to go through that. But a lot of times the RFI just answer a question. We're seeking knowledge and it doesn't cost anything. Review maintenance manuals for specified content. Review test and balance reports and other test reports as specified. Review contract as-built drawings as specified. If it's in your contract, to look at the contractor's red lines, or is it your job to actually make as-built drawings? That's kind of a big deal, so that should be in your contract one over the other. All right, let's start with select type of system. You think this would be easy. This is not easy. And you normally can't do this alone. So you got to do a system selection. Select the system may be based upon several factors, and these are all legitimate factors. Owner's mandated instructions. The owner may tell you, this is exactly the system I want. This is exactly the equipment brand I want you to use. It's his privilege, his money, his building. Match existing system type. Maybe they're trying to match an existing system, so they want it to just be an expansion. Maybe they want the most efficient system. Danger beware here. I've always said that it's great to have a really efficient building, but it's bad to be on the bleeding edge. The edge is okay, but the bleeding edge is where it's costing you a lot of money. Least costly system, that's always a problem. If you have a restricted budget, then we have to be careful of what cost is. Easiest to maintain and operate. There are places where operators are very, very scarce, so you have to have a system that can kind of take care of itself. Now, I've done some jobs in the wilderness that when you got there 2 or 3 years later, nothing worked because they didn't have anybody to fix anything. So that it would have benefited to have a system that didn't need a lot of maintenance. Well, a sound producing system. Some projects are very sensitive to sound because of whatever they're doing in the building. So your system may be determined on one that doesn't make much noise. It's not in the space, in other words. It's somewhere else with a lot of sound deadening. Maybe it's the smallest to fit in a confined space. That's a problem if you don't have much space. And that's why you as a designer need to coordinate with the architect, because the architect never gives you enough room, ever. Or they almost never put it in the right place. So if you can get early at that 35% and state your case of why you need this, especially if it's money's a problem or efficiency's a problem, then where they put things actually matters. If you put a fan room way down the end of the building, it's going to cost more to build, and it's going to cost more to operate. And sometimes architects don't understand that, so you need to help them with that. Designer's choice, that's one. Some owners say, you figure it out. You're the engineer. You figure out what system you're going to put in here. This is one I do not like. And the reason is because everyone has selective amnesia about this later on when something's not meeting the owner's expectations on your choice. So unfortunately, some designers champion systems to their preference due to ease of design effort and the resulting cost savings to themselves, or were systems championed by friends or favored vendors. This practice has liabilities for the designer if the design does not prove to meet the owner's original OPR or wishes. Best practice is to follow a documented selection process approved by the owner at each step. I've been involved with this problem many, many times, and I just can't tell you how many disasters have happened because selections of system type were made because of other reason, and this is the best for this building. It's human nature. You can't battle it, but you still should be aware this is not the right way to do it because it can get you in trouble later on. So what I'm talking about here is about selecting a system that doesn't take much for a designer. There are some systems that the vendor will design it for you. And that's where this gets into trouble, where the vendor says, yeah, I'll take care of this and I can do all this work for you, and all you have to do is put it on the drawings. And it does save a lot of work. There's no doubt about it. But it's also a problem if it doesn't work out, because the engineer of record is the one holding the liability for the job. So don't do that. Basic system selection. System types. There's ventilation-only systems. You know, if you're doing a job in Hawaii, you may only need a fan to blow air around or open the windows. Package AC or heat pump systems, which are used for smaller systems and are easy to do. Hard to fix if they don't work, and VRF system, variable refrigerant flow, is popular nowadays. Evaporative cooling with gas heat systems in some industrial applications. 2-pipe chill water with electric heat or gas heat. 4-pipe chill water systems, 4-pipe chill water and hot water systems. Radiant heating or cooling systems. Air handler types, fan coil unit, air handling unit, DOAS, etc. A lot of different types of equipment. VAV zone control with electric heat. VAV zone control with hot water reheat. Hot water zone reheat. Chill beam induction zones. 2-pipe hot water system with ventilation or evaporative cooling. Steam heat systems. So there's a lot of different types of systems. So if you want to know about some of these systems, the videos S1 through S22 cover pretty much every single traditional system. I don't have any really unique weirdos, but basically all the standard systems we've been using today and for the last 60 years, there's a video to tell you how they work and basically what the components are and what's important and what's not important about them, and what the basic sequence of operation for each one of is. So you can see those videos for that. Space requirements that affect system type selection. Space requirement, zone control, that's important. Separation of zones for temperature, humidity, or sound. Zone loading changes during occupancy. So if you have people moving around the building for whatever reason, a big conference room and they come at one time, well then that affects the load, amount of required system maintenance in the space. This is an owner's requirement. If you put hydronic heat pumps above the workspace, then for people to change the filters, they got to come into the space with ladders, going to take the ceiling apart, go above people that are working. It's not, for some occupancy, this is not an acceptable choice. Sound and vibration levels in the space. We normally don't find this out till after the fact, but designers, you're responsible for designing a system with low sound power levels, and all the manufacturers list the sound power levels of their equipment. System energy efficiency for cooling, system energy efficiency for heating, future expandability of the system. Can the system be expanded? Cost of operations and maintenance. How much does it cost to maintain this? Cost of future repair replacement, total lifetime cost. You can get a system now and say, oh, this is a really slick system going to work, but if it's got an issue that it cannot be repaired or it cannot be expanded later on, it could be a major disaster for an owner. And VRFs are this kind of system. VRFs are very efficient system in cooling. They're not very efficient in heating, but very, very efficient in cooling. But they're all proprietary, both mechanically and control-wise. So if you decide 10 years from now you want to expand that system, that manufacturer may not manufacture the system anymore, and it may not be possible. That's why I have a lot of drawbacks about VRF, is the owners on a time bomb. If something goes wrong and that vendor doesn't have that product anymore, then you have to tear out you can't just add another vendor's piece of equipment. You have to tear out the whole system. So that it's a problem. So cost and repair replacement could be what's important. So what about calculating loads? All right, calculating loads are there's different methods, and basically all this design information is available in different design manuals, and we'll go through each of those, what those are and what are available to you. So determining the methods to calculate loads. The oldest method is called the CLT method, which is the cooling load temperature difference method, and it was the first one that we developed years and years ago. This is the original method and is simplified, prescriptive approach, often used for small to medium-sized building designs. It can be used by larger ones. The problem is it can take a lot of time. So basically, we have very good computer programs to do all this nowadays. And the only thing that I caution you on is try to understand what your program is doing. How is it actually calculating this, so you can understand If it goes sideways, what happened and why, that's a problem. So you need to understand it. Based on ASHRAE CLTD data and methodology, it's available in the Handbook of Fundamentals, provides instantaneous loads for any given hour or day for cooling or heating. So you can select the hour you want to do it just by doing that hour, with making sure the occupancy is there and making sure the weather data meets that hour. You can do that. So basically, this is a system to use peak loads. You're not going to use this method to do any average loads or energy calculations. That's not going to work. Software-based RTS method, which is the next system they came up with, which is a radiant time series RTS, and its method calculates hourly heat gains using exterior weather data, solar internal loads, and then applies radiant time factors to determine how much of the heat gain becomes a load over time. Now, this is the method that was developed by ASHRAE, well, at least ASHRAE, that when I became familiar with it, is what the original heat gain programs were based upon. Now, early on, when I was in engineering, I developed computer programs to do the CLTD method because this was the only method we had. And I was doing hotels at the time, and you have a 240-room hotel room, doing 240 zones was painful. So this RTS method is what all these programs were developed on. They use that hourly weather data and is more accurate than the CLTD method. It does have more method because it tracks the energy usage over time. Whereas the first one, the CLTD, just says temperature difference. It doesn't actually track that change or the mass storage of the heat in the wall, which the RTS does. So it doesn't mean that this is inferior to this. It just means this is a little more accurate. But this is obviously going to be done with a computer. Energy modeling based, the HB method, which is the heat balance method, is an advanced computer-based ASHRAE-compliant calculation procedure that determines cooling loads by analyzing the instantaneous heat gain of all surfaces, walls, floors, roofs, and internal heat sources. It utilizes 24-hour design day simulations to account for heat storage in building materials, providing high accuracy for building energy modeling. That assumes that the input assumptions are accurate. And of course, if you put garbage in, you get garbage out. So you have to be careful with that. And this energy modeling is all based on HB methods. So we'll go through that a little bit. So watch video D2, Calculating HV Loads, to learn more about how to calculate HV loads. So we go through each of those, and we go through CLT, how you do it, so you'll understand how the process actually is. So that video will help you to understand that. It would have been a 5-hour video if I had tried to put everything in this one. So energy modeling. Once all electrical motors and energy-using equipment is selected, even as a preliminary selection, you can run an energy modeling program for efficiency considerations. You're going to verify that your energy modeling software to be used meets the sustainability reviewer approval if it's required. If you're doing a sustainable project, you're going to make sure that it meets it. And of course, the standard is the DOE Energy Plus. It's not the only one, of course. You can use a lot of other programs, but you just have to make sure that what you're using will be compliant with who's doing the review. Hourly simulation for 1 year using TYM weather data. Compare to improve design elements for efficiency improvement of the design. Calculate the cost of improvements for consideration of implementation. The energy model may have to be done several times depending on design changes during the project design process. So now most people don't use load calculation design software to do energy modeling. They're two different things. You can kind of use what I call an integrated load, like you're using train trace. You can run an energy model on train trace, but it's not really the same. You really need to use a piece of software that's designed specifically for energy modeling. Energy modeling is basically, the software is not really as detailed and robust as the design software, but they're doing two different things. So that's what I'm trying to say. The design software is trying to figure out what the load is. The energy modeling is trying to figure out how the load actually operates. So there's two different things. So then it comes time to select the main equipment type. Select main airside equipment system type to meet load requirements. So you got package units, AC heat pump or VRF. So you have package units, AC, air conditioning, heat pumps, or variable refrigerant flow, VRF. Constant volume or variable volume, those can all be any one of those. Air side economers, we're going to use that. Outside air unit or utilize DOAS units. So you're going to put outside air on each unit. You're going to have a DOAS unit. You're going to have an ERU unit. What are you going to use? That's a system top fan coil units. 2-pipe with electric heat, 4-pipe. Air handling units, 2-pipe, electric heat, or 4-pipe. Or they can have gas heat, of course. Don't have to be 4-pipe. Electric constant volume or variable volume. Air side economizers or water side economizers. That's a decision. If you have 40 air handling units, the cost of putting economizers on 40 air handling units is way more than putting a water side economizer in the central plant. Same function. As a matter of fact, unless you're in a real humid area, water side economizer will give you more run hours than a dry side economizer, than an air side economizer. But that's in a moderate to dry side ambient. Outside air on each unit or utilize DOAS units again. Energy recovery wheels or ERU units. So these are the selections you make on what kind of system and air handler equipment you're going to select to do. And this is part of your design, but you need to figure out what you're going to use there. And cost impact and energy impact is important. One problem you always have in design is if do you have more horsepower on the water side or do you have more horsepower on the air side? What I'm trying to say, if you do a job with fan coil units, you'll actually have more horsepower on the water side than you will on the air side. If you use large air handlers, you'll actually have more horsepower on the air handler side. So you have to kind of see that will affect your process on how you want to control your energy in a project is where all that horsepower is. So select water side equipment system type to meet the requirements. You got chillers, air cooled or water cooled, 1, 2, or 3 pass. A lot of times they don't talk about how many passes. The standard is 2 pass, but they do have 1 pass chillers, depending, and the difference is the amount of temperature difference you get per each chiller. A 2 pass, we normally use 10 degrees. You can go 10 to 14 degrees. 3 pass will be 15 or 16 degrees, a lot more. We're talking about 5 degrees a pass or so. So it depends on how your design's going to do. And those of the thinking about this process has changed over the years. Redundancy or standby capacity. This is one thing we're going to talk about when we talk about communicating the design. If you have a job that has 2 chillers, do you tell anybody anywhere that 1 chiller is full load and 1 chiller is fully standby? Or are both chillers required for the load? They can figure it out eventually, but it really would be nice if you just explain it to everybody right up front. Constant volume or variable volume, water side economizers, pump type and quantity for redundancy or standby capacity. It's also important for pumps. If you have 3 pumps, then there's a bunch of assumptions we're going to make that 2 of them for load, 1 for standby. Don't know, but you need to tell people that. Redundancy or standby capacity for cooling towers. Boilers, same thing. Gas-fired, electric, redundancy or standby capacity, constant volume or variable volume, variable temperature. Pump type and quantity for redundancy or standby capacity. All those things are needed. So design development drawings. Now this is pretty obvious, but we'll get to it. Mechanical drawings. This is design development, symbols and general note sheet, layout floor plans, duct drawings. Floor plans show air handler equipment and double-line duct and air distribution. That's really important because especially if we're trying to figure if things fit in space. Indicate thermostat and sensor locations. It's important that you as a designer do that. Don't let someone guess at where those are going to go. Pipe drawings, floor plans, show chillers, boilers, pumps, single line pipe less than 4 inch, double line pipe greater than equal to or greater than a 4 inch. Again, it's about fitting stuff in the space. Show all fittings, valves, and devices that indicate sensor locations. Flow diagrams for each system. Make sure that we understand how this is supposed to work. Expanded layout drawings for congested areas that really need someone to understand them, especially if some air handler duct configurations you can't figure out. Well, exactly. Is that over, under, crossed? How did this one get there to that? I have, in my life as a commissioner, I have experienced a couple of projects where the contractor got them mixed up. And all the supply grills were suck and return, and all the return grills were blow and supply. And it was, you see, how could that possibly happen? Well, it was so complicated, the fan room. And the drawings, the way the drawings showed it actually looked like the way they built it, but it's not what he intended. So make sure that's clear. Construction detail sheets to make sure we understand how to detail the actual details around a piece of equipment. Mechanical schedule sheet needs to list each piece of equipment, ID, type, capacity, CFM, GPM, horsepower, voltage, amps, everything we need to know about that needs to be on the schedule. Specification sheet, if utilized, if you got a real small job and you're not using a contractor's design spec from the architect, you're going to put everything on the drawing, then you'll need a sheet for those specifications. A control plan layout showing panel locations and network path, controller drawing sheets, control diagram, point list, wiring diagram, sequence of operation, panel layout, and material list. And all those need to be on the drawings. Then there's this thing called the basis of design. This has been around for a long, long time, but it's not terribly well understood in the industry, but it needs to be. The BOD is created by the designer in response to the owner's project requirements, the OPR. Now, an OPR may be 10 or 15, 20 pages of data, or it may be one page. Hope not. But this is the document that helps the owner transfer to the architectural design team. This is what I need. This is what I want. This is how much space I need. This is the temperatures I need. This is what I need the building to do. And it needs to be in writing. Anytime an owner assumes that an architect and mechanical and electrical designers will figure it out, is in for a rude awakening, because they will design it to their level of understanding. And if they don't understand it, then there's big trouble. I have some hilarious stories about that, but we don't go into those here. Basis design, normally produced at the 35% DD stage of design, states how the design achieves the owner's requirements as listed in the OPR, produces basic layout drawings, preliminary equipment selection, and capacity calculation summary. And of course, this would be your 35% submittal. List codes and standard utilized for the design. Includes sustainability goals and levels achieved by the design. It may include system preliminary energy analysis. Reviews how the systems was selected and alternate systems were considered and discarded. So, if how we selected the system needs to be very clear in this basis of design. Okay, here's my fun subject, communicating the design. You probably won't hear this anywhere else but here, but the drawings and specifications produced for design must fully communicate the design to the construction team, commissioners, and facility operators. The reason is the designers become intimately familiar with every aspect of design during the design process, and many times do not see that critical details of the design have not been adequately explained on the drawings. This leads to incorrect construction and poor performance of the system by operators. It sounds strange, but it's very, you know every little detail about this design, and when you lay it out on the drawings, you don't realize that you have some assumptions that you know, because you know it, but the other people won't know it. So sometimes we have to step back and look at the drawings if they have enough data. It is important that contractors or operators are not left on their own to guess what you had in mind for design details for how the system is supposed to be operated. It needs to be crystal clear, and it only takes a little note to do that. No typical, here I'll go through my list, okay, and I'll explain why. No typical areas or floors are utilized as part of the design. This, I understand, may save you a little bit of drawing time, but in the age of AutoCAD, it should not matter. The architects, if the architect does typical floor plans, shame on him. It should not be. But trying to deal with typical floor plans later on in the construction process is a nightmare. You can't keep track of what you're doing. You have to have unique numbers. And you don't have drawings to support it. You should never do it. Even if the floors look exactly alike, they're not. The rooms aren't going to be the number the same. So you need to show every floor of the job. It makes it impossible to build otherwise. All devices to have unique ID numbers, no typical numbering systems. Now, I get a lot of pushback on this, but I realize if you're doing a large hotel and you've got 200 rooms, all with exactly the same size fan coil. So you say this is fan coil A, and that makes it easy for the designer, but it causes problems later on. Remember that the owner absolutely has to have separate numbers. The control guy has to have separate numbers. The test and balance guy has to have separate numbers. So the electrical engineer needs to have separate numbers. So, I mean, basically, because of that, save a little bit of your time, costs so much time later on from everybody trying to recreate numbering systems. So just do me a favor, just put everything a number on everything. You know, even though it's the same unit, you know, you can say this is unit A14, A15, A16, and A's are all this specification. That's fine, but we need to have unique numbers everywhere. The symbol sheet clearly reflects all symbols used for the current project. Here's the problem of using a standard sheet. Many times I'll look at a sheet and say, well, what is that? And I go to the symbol sheet, it's not there. Or that symbol was used for something else. I mean, the symbol sheet needs to reflect the drawings. So that's something you need to look at. General notes are clear and apply to the current project. Current project again, if it's standard notes, you know, besides the pound to fit note, it should be unique for this project. The layout is shown in enough detail to know where it is to be installed and has been designed to be free from major obstacles from the other crafts. So if you design an air handler room, that air handler better fit in the room, or else you got the wrong room or you got the wrong air handling in it. So you need to verify that. It's not that hard to do, but you do need to do that. Layout for system zoning is clear and complete. Zoning is very important. The building's not going to work correctly if it's zoned incorrectly. Type of construction material and fitting types are clear and have been verified to be able to fit in the allocated space. Enough details are provided to clearly show how equipment is piped and ducted. All required duct and pipe devices are indicated along with their correct location and orientations. Pipe, duct, and conduit sizes are clearly labeled on all runs. No notes indicating pipe shall be the same as equipment connections. We'll see that a lot and say, well, it's just the same size as equipment connections. And then you look and you've got a branch going out, it's got 2 units on it. So that doesn't work. We need to make sure everything is labeled. Can the system be correctly built from these drawings? Pipe and duct hanger types and locations are indicated. Trapeze type hangers are actually engineered to load either by the designer, or else the designer specifically specifies that the contractor should provide those engineering services. But you can't just guess at what a trapeze hanger what you can put on it. And there's also this thing, standard codes don't allow electrical to share hangers with anybody else, which is a good thing because some contractors get really heavy, but they're intended unless it's engineered. Unless you have a hanger that's engineered to hang both mechanical and electrical off the same device and has been engineered for that load, then I think the code may accept it, may not though. All zone sensors and thermostat locations are shown. Don't let somebody else guess where you're going to put these thermostats. All humidity, CO2, and pressure sensor locations are indicated. Especially pressure sensors. I know the spec said I put it 2/3 down the duct or pipe, 2/3 down the pipe. There's a reason why we do that, and we're trying to catch any load variances. You know, if you have a couple of great big air handlers on a piping system, a couple of fan coils, you may not catch the change in the fan coil. So basically, we want them down the load, and it also does with the intensity of the reading. I mean, can you get 20 intervals? You only get 10, depending on where you take it. So that's important. All airflows and grills are registered and indicated. If you expect a balance contractor to balance it, it has to have a flow on it. If you have a job that has a lot of supply grills, a lot of return grills, and you anticipate that the balance guy has to balance the pressures in rooms, so he has to balance return grills, you need to have a CFM on it. Without a CFM, he assumes he doesn't have to balance it because it has no airflow. So that needs to be on there. All water flows are indicated for all coils and heat exchangers. Pipe and duct diagrams actually match plan and elevation drawings. Now, you say, well, why wouldn't they? Well, sometimes it gets hard. You know, you've done a diagram, a flow diagram. Oh, it's real clear there. And you go out and look at the drawing in the field and say, well, I can't figure out what's going on here. It doesn't look at it, especially for headered equipment. Duct or piping arrangements, if you've got them headered together, then that's kind of critical for that. Or decoupler piping locations. Decouplers, I see them done wrong about 25-30% of the time because the diagram is clear. The plan is not. The plan, you draw it on a diagram, it looks beautiful, right? Because it's all laid out flat. But when you go to the page, the way it's installed and the location and how the conflicts it has to go through, and they end up putting the decoupler in backwards or on the other side of the return pumps. So basically, all the water goes to the decoupler, whether it's going to the chillers or whether it's going to the field. This means you can't run them above 65% capacity of the plant. So it's really important, but it happens a lot. No typical equipment IDs are utilized to reduce engineering time. We need unique identifiers. You're on a computer. This shouldn't take long to do. Schedules are complete for all required areas. ID numbers, location, number of components, size of equipment and capacity, flows and pressures, electrical characteristics, volts, amp phase, horsepower, all that stuff. Number of pieces of equipment that are supposed to normally run in tandem for the base load. That's important that the operators understand that one machine or two machines will take care of the load, and the third machine or fourth machine or whatever it is there for standby purposes. And the other way we have to do is we have to add up all the air handling units and figure out what their load is and look at the central plant load and say, well, it looks to me like, now unfortunately diversity messes that up. So the contractor or operators can never know what the diversity really is because only you as a designer who's actually seen the load calculations, the difference between the zone load and the block load, know exactly what the diversity is. So everyone else is guessing. So you need to make sure it's clear on the drawing. So number of pumps. And remember, pumps are unique, and fans have a unique deal. Is that you have one pump and you add a second pump, it doesn't double the flow. The flow, the curves are such that it, depending on the shape of the curve, it goes down after every additional pump. I have seen some central plants that were piped. They looked like they weren't headered, but they were actually headered, and they had like 8 or 9 pumps on a header, which means basically the last couple of pumps were doing nothing. They were just burning electricity, were actually not producing any load. So multiple pumps, if multiple pumps are supposed to run together, then they need to have a multiple pump curve from the manufacturer. It tells you exactly the flow you're going to get from 2 pumps because it's not double one. Or fans, same thing with fans. Number of chillers, we need to make sure how that works. Number of boilers, number of fans. Building pressure set point. That's one thing you don't normally say, but we'd like you to tell us what pressure you want this building under. And normally buildings need to be slightly positive, so between 0.01 and 0.03. 0.02 is what I like to use, is right in the middle. Now, 0.02 inches of water, not very much pressure, but there is some. Especially if you happen to have a building that has cascading pressures within it, say if it's a medical facility or something where we have to have pressure differentials between hallways and buildings and rooms from one room to another room to the outside. And then it becomes critically important that those building pressure points are shown and you tell the tab guy exactly what you want that building to be. Items for maintenance and operations, make up water pressure setting. That would be really nice if you would tell the operator that this building needs to have 35 psi of makeup water because it's 90 foot high. So the makeup water pressure, normally the operators don't know how to set it. Most people say, oh, you set it at 12 psi. No, you set it off the height of the building. So it needs to be done that way. Pipe tests wells for temperature sensor calibration. If you have a critical facility that you're doing that needs to have calibration done periodically, then pipe wells are a problem for calibration because to do it right, you need to have 2 wells, one for the instrument and one for a test instrument, right near each other so they can read the same. Duct test tap seals and specified to be plastic or stainless steel, depending on your type of facility. So air duct design. So now we'll talk about design a little bit. These are another video, of course. Normal duct velocities and pressure class. Okay, To do this video, I went back through all my documents and my standards and realized that some of the standards are older and have not been quite updated. So duct pressures and velocities has changed greatly over the years. When I first started, it was nothing to have a medium pressure system running at 10 inches static pressure, what we called high velocity duct systems. Yeah, you will never see that today because the horsepower and sound from that is horrendous. So nowadays they're changing. So this low velocity branch duct was originally 2,000 feet per minute, and it's plus or minus a half inch static pressure. Still that pressure, but you won't be sizing anything at 2,000 VSI. The really velocity is 600 to 900 feet per minute at point. And normally, if your size for duct is at 0.08 to 0.10 inches of loss per 100 feet, so that's where you're using friction. And normally you will lay out your duct using friction, and then you'll use a computer program to bring it all into the depth and do static regain or whatever. But normally you're sizing it off of a ductilator or something. Medium velocity, low pressure main duct was 2,500. Still that velocity is too high. But 2 inches, plus or minus 2 inches is still adequate. Normally you'd keep velocities between 1,000 and 1,300 feet per minute. Still size around 0.08 to 0.01. High velocity medium pressure duct, we call it high velocity, but it's really not. It's a 4,000 or down, and again 4,000 is too high, but the 4-inch static pressure is fine. So normally we'd size those between 1,000 and 1,600 feet per minute, and the reason is we're worried about noise and we're worried about energy, and energy is directly coupled to pressure. So the more pressure a fan has to produce, the more energy your building is going to use. So low pressure is the holy grail of energy and sound. This high velocity duct makes a lot of noise in the space. High pressure industrial systems, which are 6,000 feet per minute and 10 inches, plus or minus 10 inches, are mainly for industrial and for transport services. Transport services means that you're using the air to transport material. Or industrial might be, 4,000 feet per minute because of big duct. The larger the duct, faster the velocity can be because it's got a bigger cross-sectional area. And we'll talk about that during the duct design. Ducts are sized by one of the following methods. Equal friction, which is 0.08 to 0.1 inches per 100 foot of duct, is the normal area that you're going to select it from. However, there are other areas. So equal friction methods sizes all duct at similar friction rates, with the smaller applying to air flows at 0.08 to 0.1. For higher flows, larger mains may be sized at 0.1 to 0.15, and returns are normally sized at 0.05 to 0.1. So the suctions are sized lower velocity because a fan is more susceptible to disruption on the suction side than it is the discharge side. So you want to have a nice even flow on the suction side. You want to have it on the supply too, but suction is actually more critical. Velocity reduction may maximum be at the fan. The velocity reduction method reduces the duct air velocity in small amounts starting from the fan outlet down the duct run. Never allows velocity to increase, which will cause system effect and increase fan horsepower. So what we're saying, if you size a fan, the fan's got a leading of 1,800 feet per minute, then you will start sizing ducts for slightly smaller feet per minute as you go down the duct run. That's hard to do, especially if you've got a zone system where you've got BAV boxes in it. Then it won't happen because you're going to have to increase the velocity at the box, at the control device. Any control device will increase the velocity of whatever's happening. So we will talk about it in these pipe design and water air design videos. But basically, system effect is any time you have a situation where the velocity is increased. Because remember, velocity pressure takes fan horsepower to do. Static is free. You take a fan, you blow the air up, you get two components. You got velocity pressure and static pressure. And as the air starts going down the duct, the resistance of the duct starts slowing the air down, thus decreasing the velocity but increasing the static pressure. It's called static pressure regain. And you get static pressure regain for free. Increasing velocity costs you horsepower. So all you got to remember is don't ever do something like a fitting or something that has a lot. I will explain all this in the duct, but it basically means it's system effect, and we don't like that. That's not good. So static regain. The static regain method for duct sizing. Sizes of duct run so that the increase in static pressure due to the reduction in velocity at each branch or air terminal just offsets the friction loss in the next section of duct. This method tries to provide the same static pressure at each branch or takeoff. This is a good way to design duct. It's laborious if you're trying to do it manually because you have to do a lot of calculations, but they do have static regain duct sizing programs that will size it for you and regain. But remember, it will do this within certain bounds. If you do something stupid, it won't fix that. So you got to watch what you're doing here, but the whole process here is trying to get equal pressure at outlets. And it does work. I have had a job or two in my career early on that had to have equal pressure. It was an industrial job, and it was very critical. So I did it by hand. It was a large duct system, and we actually put in orifice plates where we knew we were going to have to eat pressure up for something, and it basically, when you turned it on, it was already balanced. It was self-balancing. But boy, did it take a lot of work. You could do it nowadays with a computer program. It wouldn't take as long, but those are the three methods: equal friction, velocity reduction, or static regain. The way I do it nowadays is I use equal friction and velocity reduction kind of combined, but equal friction is really ruling the roost. For me, it's just easier. Duct sizing for equal friction and velocity reduction methods are normally done on a ductilator, while computer duct sizing software should be used for static regain due to the amount of calculations. Doing it by hand is just crazy. So watch video D3, which is the air side equipment and duct design. This one will go through all the duct design and what to do and how to do it. And it's a fairly long video, but it will get you through duct design. So let's talk about pipe design. So pipe sizing calculator tools or apps. Engineering toolbox charts and calculators, those are online. Pipe sizing by Caliphate Hydronic Solutions, that's one I've seen. HVAC Pipe Sizer Plus by Carmel Software. These are basically apps. Many others available. There's tons of available. Pipe sizing software, Train Pipe Designer, Carrier Design Suite, eDesign Suite, McQuay software for HVAC pipe sizing. I assume that the Dankin has kept that current. There are others. Pipe design drawing software, so 3D piping design software tools, Smart 3D. That's available. PDMS, Plant Design Management Software by Alvent, and PDS Plant Design Software by Hexagon. CADWorks Development by Hexagon. AutoPlant Development by Bentley. AutoCAD Plant 3D by Autodesk. Now, I'm not familiar with most of these softwares. I did find them. I know up around trying to find tools for duct sizing and pipe sizing on an app for your phone are basically junk. They'll tell you some basic things, but they're not really very robust. You can find it, but anyway, I'm just trying to tell you, they're out there. You can find them, make it easier for you. But when we go through our design examples, we use the methods shown in ASHRAE and other manuals. We'll go through those instead of counting on these apps. So you can watch the video D4 for water side equipment and pipe design. It goes through all the aspects of doing water design. We use similar techniques for both pipe and air, but remember the difference is water is not compressible, where air is. It actually makes a difference. So you got to learn those different aspects. Design activities during construction, as long as you have service requirements. Provide engineering field services as contracted, attend on-site meetings, perform site inspection and post reports as contracted, review contractors' equipment and drawing submittals, designer to approve submittals as it's meeting design capacity and size requirements. So someone say they don't approve them anymore, they just say reviewed, fine. But what it means is whether they like it or not, they've approved it. verifies submittal equipment and material meet specifications, answers RFIs from contractors, responds to commissioning and tab reports, review contractors' maintenance manuals, reviews contractor as-built drawings, create as-built drawings from contractor red lines if contracted to do so, review annual energy consumption and energy model if contracted to do so. That's the basic design process. I know it was kind of a whirlwind, but it has all the basics you need to do. You just doesn't detail. I didn't explain all the details because the video would have to be 14 days long. But anyway, I really appreciate you watching the videos. I hope this was beneficial, and I hope you really enjoy the duct design and load calculation, duct design, and pipe design modules. Again, man, have a great day, and I really appreciate you watching them. Keep it up. Talk to you later. Thanks.